Доброе утро, уважаемые участники конференции, дамы и господа. Guten Morgen, meine Damen und Herren. Good morning, ladies and gentlemen. With my pleasure, I kindly invite you and welcome you to the Moscow University of Technology, Stankin, where today we held a plenary session of our International Technic Conference, Advanced and Concurrent Manufacturing Technologies, which we held together with the Institute of Machine Tools and Manufacturing of Federal Swiss University of Technology and Stankin. And this conference is devoted to the 19th celebration of foundation of Stankin. You know that this conference previously should be a year ago, in September 2020. But due to situation with the pandemic of the coronavirus, we changed the time of our conference for this time, for the end of May, beginning of June, for the reason to combine it together with our main exhibition, металлообработка, machine working industry, which was in Expo Center last week, and today the science. You see, unfortunately, tomorrow in St. Petersburg starts an economic forum. And all of officials were going to this forum, but anyway, we received a letter from the Ministry of Science and Higher Education, and I ask very shortly introduce with greetings for our conference, please.
Dear participants of the conference, Advanced and Competitive Manufacturing Technologies, digital transformation is one of the national goals of the Russian Federation. Another one is to increase the export of non-primary and energy-safe goods. To achieve these goals, both effective staffing and the formation of the scientific and technological groundwork in the field of production, primarily in mechanical engineering, are necessary. Experience shows that work in both directions is impossible without international cooperation and interaction within leading technological countries. Today's conference has an international status and especially important as a symbol of victory over the disunity and limitations caused by the pandemic and political factors. Focuses on the experience exchange on a very important issue for both Russia and the world. What promising technologies it makes sense to take into the future for the high-tech mechanical engineering sectors. Its organizers are Moscow State University of Technology Stankin, the Higher Technical School of Zurich, its guests of honor, primarily the president of the Fraunhofer Society, Professor Neugebauer, are leading centers of applied science representative. And here we can say that we are greeting all the participants and speakers of the conference on behalf of the Ministry of the Education and Science of the Russian Federation and wish you productive work and the development of long-term cooperation which occurs where there are interesting topics for discussion and high concentration of enthusiastic professionals. This atmosphere for sure reigns within the walls of Stankin today.
And now, with greetings, I would like to introduce our rector, Professor Kapitanov. Please.
Уважаемые участники конференции, дорогие друзья, гости, я рад приветствовать вас в стенах Московского государственного технологического университета на пленарном заседании Международной научно-технической конференции «Передовые, конкурентоспособные производственные технологии». Эта конференция, как уже было сказано, организована нашим университетом совместно с Институтом станкостроения и технологий машиностроения Высшей технической школы Цюриха. К сожалению, как было отмечено, текущая эпидемиологическая ситуация не позволила сначала нам провести эту конференцию в прошлом году. Сегодня она вынудила нас провести ее в смешанном формате. Но, несмотря ни на что, я спешу сообщить, что всего на конференцию зарегистрировано более 100 участников из 14 стран мира, что в текущей ситуации, мне кажется, весьма достойный показатель. Да.
Dear participants of the conference, honorable guests, our friends, ladies and gentlemen, we are very glad to welcome you in Moscow State Technological University Stankin on the plenary session of International SciTech Conference, Modern Competitive Manufacturing Technologies, held by our university in cooperation with the Institute of Machine Tools and Production of Higher Technical School of Zurich. And it is also dedicated to the 19th anniversary from the foundation of Moscow Technical University Stankin. And unfortunately, current epidemiological situation made us hold the conference in a hybrid format. And all in all, to our conference, more than 100 participants from 14 countries were registered.
Мы благодарны нашему учредителю, Министерству науки и высшего образования Российской Федерации, за поддержку в проведении нашей конференции.
We are very grateful to the founder of Ministry of Science and High School of Russian Federation for support and participation in this conference.
И, безусловно, особую благодарность хочется выразить нашим зарубежным гостям и участникам конференции.
Well, and we would like to give special thanks to our foreign guests and participants of the conference,
которые, несмотря на имеющиеся сегодня сложности и ограничения в передвижении между странами, нашли такую возможность их преодолеть и лично смогли посетить Москву и наш университет.
who, in spite of all the complexities and problems in traveling between countries, found the opportunity to come to Moscow personally.
Особую признательность, конечно же, хочется выразить президенту франкоферского сообщества профессору Нойгебауэру и директору Института станкостроения и технологий машиностроения профессору Вегенеру. Пользуясь случаем, хотелось бы отметить, что для нас особо почетно, что наши гости при всем прочем являются еще и почетными докторами МГТУ Станкин.
We are very grateful to our honorable guests And we would like to tell them that we give them special thanks. Especially to President of Fraunhofer Society, Professor Neugebauer, and Director of the Machine Tools and Production Institute of Swiss Technology School, Professor Wegener, who are also honorary doctors of MSTU Stankin.
Наш университет Станкин был образован в 1930 году и изначально решал задачи, связанные с развитием и созданием и развитием отечественного станкостроения.
Our university, Stankin, was founded in 1930 for solving problems of developing and creating home machine building. Now it is called mechanical engineering.
Эта задача была, безусловно, успешно выполнена.
And this assignment was successfully completed.
Сегодня, спустя 90 лет со дня своего образования, наш университет остается ключевым, ведущим отраслевым вузом.
Well, since 90 years after its foundation, our university stays key and maybe leading university in its branch.
Несмотря на то, что мы являемся довольно небольшим с точки зрения показателей университета, как вы видите на слайде, это порядка 5000 студентов и аспирантов, в том числе почти пятая часть, 800 человек, это иностранные студенты.
Well, in spite of the fact that our university is rather small, we have only 5,000 students and postgraduates, including 800 foreign students and from 65 countries of the world.
Но при этом мы являемся весьма хорошо оснащенным технологическим университетом с хорошо известными научными школами и выпускниками.
And we are still a very well-equipped technological university with well-known research works and our graduates.
При этом выдающимися выпускниками являются не только представители научно-технического сообщества, но и, как можно увидеть на этом слайде, люди, достигшие высот в таких областях, как госуправление. Среди наших выпускников есть председатель правительства Российской Федерации и вице-премьер в том числе.
So among our graduates, there are the representatives of our government and even Prime Minister.
Структурно наш университет состоит из 4 институтов.
Structurally, our university consists of 4 institutes.
Соответствующие специальности отражены в их названиях.
Well, and congruent specialties are seen in their names.
Как вы видите, кроме отраслевого станкостроения, мы также работаем в области информационных технологий, автоматизации, робототехники, разработки технологического оборудования для различных отраслей машиностроения.
Besides mechanical engineering, we work in the sphere of information technologies, automation, robotics, and developing technological equipment for different branches of machine building.
Научные исследования наш университет проводит в 17 научных центрах и лабораториях. Я могу отметить несколько научных направлений и лабораторий, они кратко изображены и отмечены на слайдах. Это лаборатория аддитивного производства и метрологии, лаборатория заготовительного производства, процессов обработки.
Research work takes place in 17 scientific centers and laboratories. Well, we can pay attention to the following trends and laboratories: additive production, metrology, well, blank production, well, machining processes, and so on.
А также нанопокрытий и исследований свойств материалов.
And also nano coatings and analysis of material properties.
За последний год в высокорейтинговых журналах из базы Web of Science и Scopus сотрудниками университета в соавторстве и без опубликовано более 250 научных статей.
Well, for the last year, in such high-rated journals as Web of Science and Scopus Base, there were published more than 250 research papers.
Выполнены исследования по наиболее актуальным направлениям разработки и внедрения аддитивных технологий для изготовления изделий из композиционных материалов.
Well, there were fulfilled research work and actual trends developments in the implementation of additive technologies for making products from composite materials.
Наноструктурированных многослойных покрытий на режущий инструмент.
Nanostructured multi-layers coatings on the cutting tools.
В области разработки конструкций новых станков и металлорежущего инструмента.
And in the sphere of developing new production systems and mechanical engineering.
А также имитационному моделированию производственных систем в машиностроении.
And also imitation modeling of manufacturing systems in mechanical engineering.
Я уверен, что наше мероприятие, наша конференция внесет новый ощутимый вклад в развитие современных производственных технологий, а также, конечно, укреплению сотрудничества между партнерами.
I'm sure that this conference will make a great contribution to the developing of manufacturing technologies and strengthening cooperation between partners.
Я желаю всем участникам конференции успешной и, самое главное, результативной работы. И, конечно же, здоровья. Спасибо.
I wish all the participants of the conference successful and fruitful work, and of course, health, good health.
Thank you very much, Professor Kapitanov, and let's go on. I would like, it's my pleasure, to present and to introduce our dear guest, the president of Fraunhofer Society, professor and doctor and honorary doctor of Stankin University, Raimund Neugebauer. Please, with keynote speaker. You can use a clicker, yeah, and every is here.
So, good morning, ladies and gentlemen. And thank you, Professor Kapitanov and André, for the invitation to this conference here. It has been far too long since I visited you here at Stankin University. Also, my path has not led me to Moscow very often in the recent years. Our two institutions can look back on a continuous and successful cooperation that began in the 1980s. I'm thinking, for example, of research projects in the field of the finite element method, followed later by projects on innovative grinding technologies. We also joined forces in research projects for the Federal Ministry of Education and Research and the Deutsche Forschungsgemeinschaft, focusing on environmentally compatible production technologies and the energetic design of machine tools. I'm very pleased that our cooperation has remained stable and that our two major research institutions have repeatedly reaffirmed it. As an example, we signed a memorandum of understanding in 2013 that defines applied production research as a common goal of our both institutions. However, the cooperation that we put into practice is more important than written agreements. Our society is facing global social and economic upheavals. To address these issues, science and research can develop solutions, open up synergies across borders, and act as an integrator. In my presentation, I would like to point out how the Fraunhofer Gesellschaft, with its strategic research fields, is facing these challenges. I would like to divide the presentation into 4 sections. At the beginning, I would like to give you a short insight about Fraunhofer and our global activities. After this, I will briefly talk about recent technological drivers in production engineering. Based on this, I will show you some selected solutions from Fraunhofer for these drivers and challenges, and I will conclude with a brief outlook on the end on what the long-term development in this area, in our area, the production research, may look like. The Fraunhofer Gesellschaft, next slide, the Fraunhofer Gesellschaft is headquartered in Munich, is Europe's leading applied research organization, and which is focused on developing key technologies that are vital for the future and enabling the commercial exploitation of this work by business and industry. Fraunhofer plays a central role in the innovation processes, and you can here see in the chart on the left side, we have at the present time a staff of 29,000 co-workers, and here employees or co-workers, 75 institutes, and the 75 institutes, we have more than 100 locations in Germany. It's a high willingness by the states to have Fraunhofer institutes for the push, for the innovation push in the industry. And you can see here, we have a budget around about 3 billion, was a little bit less in the last year because we have problems also by Corona crisis, and 2.4 billion are contract research. And very important, our Fraunhofer model is subdivided. We have 3 parts of research and 3 parts of financing. The first part is a base funding from the Germany's federal and state governments is around about 650 millions. And the second part is that we win, or that we organize in competition to other organizations in public programs by European Union, by the federal government, by the state governments. We call it pre-competitive research with the industry. And the third is direct innovation push, exclusive for companies and paid by the companies. And this model is very, very suitable to bring innovation push in the industry. And that is the reason that the states want to have Fraunhofer institutes. And we increased in the last 6 years by 10,000 researchers and 1 billion euros in the last 6 years. And here you can see our international activities. Outside from Germany, we have 8 independent Fraunhofer affiliates. In USA is the oldest. We started in USA in different places in 25 years before. And in Sweden, in Austria, Portugal, in Europe, in Italy, in Chile, in United Kingdom, and in Singapore. Additionally, we have 12 Fraunhofer centers, also in Austria, Italy, and Portugal, and Sweden, and United States, and Chile, and in Singapore. And the Fraunhofer centers are the columns of the Fraunhofer legal entities abroad. And furthermore, we also established 13 Fraunhofer project centers or innovation platforms in Canada, Brazil, Ireland, Netherlands, Poland, Japan, South Korea, Israel, China, and South Africa. And maybe in the future, Professor Kapitanov and Professor Professor Kutin, we could also organize a Fraunhofer project center. It's a temporary organization with researchers from our partner country and Fraunhofer in a common research in a common goal, and the efforts are financed from the German side by the Fraunhofer by the German side and from the partner organization from the partner country. Maybe we can also organize as a sign of diplomacy by science, such a center together here in Moscow. So overall, we have active cooperations in 80 countries. After this short introduction, I will now move onto the technical part of my keynote, and I like to begin with a brief overview about the recent challenges and drivers in production engineering, which every one of you also experience. So I think so in our daily business. But I want not to forget to congratulate the university. Last year you have had the 90th anniversary. And it's not too late, but I will now give our congratulations also from the German side before I start in the technical part. And now you can see here in our eyes, production technology has traditionally been and still is the backbone and engine of industrial value creation. It's very important, I think, also for your country in Germany soon. Thus it has always been subject to change and needed to continuously adapt to new production technologies, new products, regulations, and economic aspects. In recent times, 3 key drivers have moved even more into the focus of production technology: digitalization, resilience, and resource efficiency, driven by economic and sustainability factors. The COVID-19 pandemic, however, has shown us vulnerabilities of modern production systems and global interdependencies also. This also provided an opportunity to develop approaches for future improvements, where digitalization, resilience, and better resource management also play a key role. And these 3 fields, digitization, resilience, and resource efficiency, are also the main focus of our activities. And I spoke we have had a pre-discussion with the rector, Professor Kapitanov, and my recommendation as a member of Stankin, because what Andrei mentioned, I got the honorary degree like Konrad, but Konrad 16 years before you. But I think a very good meaning recommendation from my side is the university can not only look in the future to combine mechanical engineering with IT and digitization. We have also to look to the energy problem. And I've had in my own institute in Chemnitz and Dresden 15 years before projects where we looked to the energy consumption of machine tools. And also partners in the industry told me, it's not important. You can go with your project. Today, the energy consumption of machines is a great precondition for good sales of the machines. And I think this is an important new field also for Stankin in the future, to look of energy efficiency and new energy using, also energy of renewable energies in machine tools and in production systems. This will play also a key role in the future. And with the ever-growing trend towards individualization of products, however, an increase in efficiency is no longer determined by an increase in process speed, but depends decisively on the speed flexibility and reconfigurability. It's also for a German not easy to speak English, on the process architecture. Here digitization is the key, and it allows for digitally supported and highly variable manufacturing methods that are becoming increasingly important for producing individualized and complex goods in an economic manner and being able to quickly adapt to change. And here is a chart from our CIRP colleagues. Konrad and Andrei Kutin know the colleagues. You can see here Professor Koren from United States, Spitani from Israel, and other colleagues. They showed in the chart, we come back to the early beginning of production technologies. A high number of products, but every product have other design, other materials, and so on. And that's the challenge, and we can realize this by individualized mass production in the future. And the precondition for this are to use the digitization in production technology, and especially additive manufacturing is a great precondition for this. Resilience is the ability of a complex system to quickly return to its initial state despite massive, unexpected disruptions, possibly even in an improved form. We in the Fraunhofer Association or Fraunhofer Society, Fraunhofer Gesellschaft, we work since a lot of years in the field of resilience. But in the first time, resilience was a challenge in infrastructures, in the public life. And now resilience is, after the crisis, also very important for production systems and in the industry. And you can see here our concept, and the Fraunhofer concept especially emphasizes the concept of resilience engineering, dealing with the important question, how can we increase the inherent resilience by design for technological and production systems, infrastructures, supply chains, and economic activities to remain at the best possible operational level, even in the face of disruptive events. And you can see here we have to look to prepare the event, to dampen the dangerous situation, and recover and come in a better situation, improve the situation after the crisis in the system or in the technical system or in the complete production organization. And the third challenge, the classic manufacturing, it's not the third, is also resource, is also resilience. You can see here in this chart what are the challenges on the left side and what could be the solutions on the right side. And also here you can see energy plays a key role in the future. Energy efficiency as the first step, and energy security in the second step, when we have a disruption in the energy grid, for example. And you can see other steps, bio-based materials and processes. I will show this in the next charts. And circular economy is a great challenge. Carbon dioxide reduction and the utilization of carbon dioxide after using the carbon dioxide from processes. And lightweight components is an old field where we all work since a lot of years, but we have to realize it more strongly in lightweight in a circular economy. And additive manufacturing is the topic here in the conference. Biological inspired technologies, research, efficient computing is also a great challenge. We work in the European Union in a circle. It's called Euro HPC, Euro High Performance Computing. And in this club, let me say a club, or in this group, a lot of countries, or the objective in this group is to build up a European ecological system for high performance computing. And in the first wave was organized that 5 states got a high performance computer with teraflop, on the teraflop level. It was in Luxembourg, in Czech Republic, in Slovenia, I think in Greece or Bulgaria. And in the second wave, petaflop computers are installed. It's realized in the present time in Barcelona, in Bologna, and in Finland. And in the third wave, in the next year, on the end this year, starts the third wave, we get exascale computers in Germany and in France. And the exascale computers have an energy consumption, it's like a factory. It's very high. That means we have also to look for solutions for energy, for low energy computing in the future when such high performance computers are combined with production systems. And the next chart here, this was to the energy efficiency, and what I here have on my written down on my cards. Question is also, we use artificial intelligence for very strong for production systems, and this leads to this high energy consumption. And in the following, I would like to show you how the 3 thematic blocks, additive manufacturing and biological transformation and digitization for remote manufacturing is a new buzzword, also remote manufacturing after the crisis. How can we find solutions for these 3 challenges? And at first, and you can see here in this chart, additive manufacturing is being introduced with a growing number of application areas and brings many advantages. Examples from Fraunhofer you can see here in this chart. On the upper left, the fast and decentralized production of equipment like emergency ventilators for the treatment of corona patients. We realized this in the last year. Very decentralized in Germany and in Europe, we produce different components. The possibility to manufacture complex customized parts from various materials on site. Even biological materials like cells can be printed, which is the first step towards personalized transplants without the danger of immune reaction. We realize this in Würzburg, in Bavaria. We print cell material, you can see it on the right, and for example, for artificial skin. The layer-wise build-up on the left lower part of the structure allows for multi-material matrices, and even the integration of microelectronics and lightning components. Very interesting, the combination and the integration of microelectronics and lightning components. And also the space industry on the right lower part got interested in additive manufacturing, for example, for building low-cost microsatellites for someday even structures from regional resources like lunar soil or regolith. You know the regolith. Regolith is the first layer in the planets which we can use in the future for components out of the Earth. The next chart. Also, the potential of 3D printing has been demonstrated. The technology is still not fully mature and established. What are the challenges? Fraunhofer is addressing such major challenges with within its lighthouse research project, Future AM, to close the gaps that still hinder AM from becoming part with a smooth and continuous process chain. Konrad, maybe you are an evaluator of this project? Okay. You know more like I. The project includes solutions for establishing compatible data formats, enabling a consistent linking of digital and material process chains, improving scale-up, multi-material range, and faster build-up rates, automation for post-processing and quality assurance, and the development of novel software for automated AM components, identification and optimization. Only the consolidation and holistic development of additive manufacturing will achieve the necessary progress for end-to-end economy or economic viability and industrial cross-sector maturity, thus resolving the trade-off between flexibility and profitability. I think you can see the examples here in the chart. And the next topic, the idea of the biological transformation, was established in the last couple of years to bring new solutions from specialist disciplines outside production engineering to solve the problems in the production engineering. And I self can say I was one of the main drivers, Konrad, you know this, also in the International Academy of Production Engineering, CIRP, for this field of research in production technologies. And let me give some deeper information about the approach. Through billions of years of evolution, nature has developed many solutions that can serve as model for efficient and effective technologies. These can be material properties, for example, lotus effect, structural colors, biocompatibility, or the material composition of mother of pearl or spider silk with extremely stable lightweight properties. Structures and shapes, for example, for very good aero or aquadynamics, but also general concepts of nature such as network communication, nervous system, neurons, self-organization, swarm intelligence. We use swarm intelligence, for example, for logistics in factories, but also for milling strategies in machine tools by swarm intelligence, self-healing, homeostasis, and our circularity process. Over time, animals and other organisms have developed sophisticated survival and adaptation strategies, for example, to camouflage themselves, to get by with as few resources and energy as possible, to protect themselves against attacks, and to survive under adverse conditions. From an evolutionary point of view, all living beings that exist now can be regarded as models of success in design, materials, energy consumption, and so on. Illustrative examples within the biological transformation are materials like spider silk, bio-based raw materials as substitutes for fossil-based materials, for example, in plastics. Structures, nature has developed stable geometries such as snail shells, strong and lightweight constructions like bones, as well as aerodynamic shapes or nanostructures for adhesion like gecko feet or for weather-resistant colors of butterfly wings. And processes, the third part, like the efficient communication between synapses, immune systems like protection against external attacks, or evolution itself. These solutions can be categorized according to the degree of integration of biological components. Inspiration, on the right. Biology is considered as a model for technology or processes. Integration, biological organisms and components components are integrated into technology, for example, for actively producing materials or fulfilling specific tasks, and interaction. In this case, biology and technology interact and communicate with each other, like as it is the case with brain-computer interfacing, for example. As one bigger example, facilitated variation. Facilitated variation is a special evolutionary biological theory which combines findings from micro, cell, and developmental biology. Facilitated variation explains how nature efficiently creates useful diversity to adapt to changing needs. The figure on the right showing birds with wings, but for totally different purposes. Facilitated variation cannot be expressed by several equations that can be applied directly to solve the adaptation, flexibility issues of technical systems. But it serves for a new way of thinking, holistic consideration and optimization. Facilitated variation tells us how to implement traditional artificial intelligence algorithms in this new context. The implementation strategies are oriented along the 4 core aspects for facilitated variation: explorative behavior, weak coupling, conserved core processes, and invisible anatomy. And now I have an example where we can use facilitate variation. It is much more efficient to perform the evolution in the digital world than producing and measuring numerous real samples. But the simulations need to be validated. When considering nature-like behavior, the digital twin concept needs to be extended. A natural being is always in exchange with its complete environment. The digital twin only knows a predefined set of specifications. The example shows the milling process of a turbine blade. The specifications comprise roughness, shape deviations, and shutter marks. By introducing the concept of the digital environment, the performance of the instances can be evaluated directly in vivo, like in nature. See example, the digital twin of manufacturing performs within a computational fluid dynamics environment on the right side. The outcome of the imperfections, like shatter marks, influences the airflow directly and enables statements on higher level goals, like degree of efficiency, fuel consumption, etc., in the later acting of the components. The holistic digital environment model requires very high computing capacities. On the other hand, the complexity of the problems can be decreased by conserved core processes. It's a very interesting approach in my eyes for the future. And now to digitization for remote, some words about remote manufacturing. How I mentioned at the beginning of my presentation, remote manufacturing is a result of the reaction to the corona pandemic in the last years. And the question is to minimize the personal contact in production companies. Whereas most office workers were able to continue their duties from home during 2 lockdowns, many factories had to close down or drastically reduce their workforce. experience from my own company. In the institutes, we have had, during the hardest time of Corona, a presence around between 30-35% until 50%. In the headquarter, we have had 15 until 20%, because in the headquarter we have administration. But the institutes need the labs, and in the labs you need the people. And in the companies in Germany was similar to the institutes. Therefore, the questions arises if factory workers could someday also take advantage of remote work. That's the question. Can we organize remote work for the co-workers, for the workers? For manufacturing industries, this could allow for an increase in productivity, improvements in safety and ergonomics, as well as work flexibility and globalized recruitment of skilled workers without the crisis. However, remote operations in factories are much more challenging than in offices due to their significantly higher complexity, coordination and timing requirements. Totally new operation models in manufacturing have to be developed for production with limited on-site presence. However, the technologies in this context of Industry 4.0, new possibilities can open up. For example, low latency infrastructures. We work about 5G, and next time 6G. Sensor networks, Internet of Things, and digital twins. I think so most of you know the principle of the digital twins. Considering condition monitoring, cognitive robots, virtual and augmented reality, and cybersecurity, as well as data protection and trusted electronics. Trusted electronics is a great challenge for us. In the next chart, you see the 5G Industry Campus Europe. It is the first site in Europe to have a comprehensive 5G network to explore and test new applications for 5G in production environments under real-world conditions. With an outdoor network of around 1 square kilometer and a shop floor of 7,000 square meters, the 5G network will cover the area of the RWTH Aachen, Campus Melaten, and the entire machine hall of the Fraunhofer IPT. To ensure that the results are transferable to industry, the 5G network will be set up to cooperate within a frequency band of 0.7 to 0.8 gigahertz and will additionally have access to a 5G network. A variety of use cases can be explored and tested on-site, for example, multi-sensor, you can see it on the left lower part, multi-sensor technology for the transmission of massive data with low latency requirement, for example, for real-time monitoring, testing the limits of a completely wireless 5G blockchain utilization, 5G logistics and coordinating autonomous systems in a supply chain, 5G robotics and robot communication, distributed remote monitoring of machines and processes with 5G and factory 5G cloud and edge cloud technology. And now some words about artificial intelligence in this context. Artificial intelligence, AI, has the goal to develop machines like computer or robots that show dimensions of natural intelligence. This includes cognitive abilities like perceiving sound, recognizing visual inputs, communication skills with humans, being able to learn and make decisions, adapting to changing environments, and taking safe actions. Sometimes in Germany and in Europe, I hear that the colleagues, when they use an algorithm for machine learning, they speak about in artificial intelligence. It is not artificial intelligence. It's a part, one topic of artificial intelligence. AI could contribute up to 15.7 trillion US dollars to the global economy and cause a boost in GDP of up to 26% for some economies by 2030. Various analysts estimate the global market size for AI in manufacturing to be around 16 billion US dollars by 2025. So the forecast. However, there are still some research challenges associated with AI. The energy consumption, especially for machine, the energy consumption, especially what I mentioned for machine learning, needs to be lowered significantly. The models and results generated by AI tools needed to be reliable, safe, and trustworthy. Both goals can be achieved with a technique of informed machine learning. In this case, we combine a hybrid technique by data-driven methods like deep learning and knowledge from physical laws or experts. This decreases the data requirement for model generation as well as processing resources and leads to more plausible and trusted models. And now I finish the technical content-related part, and I like to close my presentation with some short brief words to the outlook. Production technology, I think, is also in the future a fundamental basic for the society and industry, and will be the backbone also of value creation. Digitization is very essential for innovative and competitive production engineering, and the biological transformation can help us for decrease material consumption, decrease energy resources, and also decrease the influence, the impact to the environmental and the climate. Thank you so much for your attention.
Thank you very much, Professor Neugebauer. Please stay here. Please stay here, because I would like to announce a ceremony of signing of a memorandum of understanding between Fraunhofer Society and Moscow State University of Technology. Please take your seats, Professor Kapitanov and Professor Neugebauer. And ladies, please, our students will help us.
I signed for Switzerland. You have to pay.
Профессор Нойгебар очень любит шутить, и он сказал, что он будет подписывать за Швейцарию, так как флаг. Это тоже очень хорошо.
Professor Capitano, it's my pleasure that we sign the MOU. Is a difference in the signing procedure. On the side of Stankin, it's enough when the rector signed. On the side of Fraunhofer, we need a second signature. So, we'll make a shake hand. Professor Kapitanov, thank you so much.
Thank you.
Thank you very much, professors. We can. Yes, you can leave it here. Thank you very much.
Thank you.
Take your mind step. Now I would like to introduce our colleague, our good friend, Professor Konrad Wegener, the director of the Institute of Machine Tools and Manufacturing of Swiss Federal University of Technology. Please, Konrad.
Dear Professor Kapitanov, ladies and gentlemen, it's my great pleasure to speak here on behalf of the Institute of Machine Tools of Manufacturing and Machine Tools and Manufacturing. And I just want to start with somehow like a comparison, dear Raimund. I must say we are approximately 300 times smaller than Fraunhofer. And it is really difficult to speak after my dear colleague, Professor Neugebauer, because he graced totally the field. So actually everything is said. So the only possibility that I have is to go a little bit more into some details, and this I would like to do. So the question is, what happens after Industry 4.0? It left behind a lot of scientists and engineers and industrials looking a little bit puzzled around what can we do with that and what might be the future outcomes of this new approach of technology. And I want to share with you some thoughts on what is a machine tool of the future. I frequently point out that the machine tool is the enabler per se to make to create wealth, to make goods, and therefore any technology that is invented should be applied somehow to machine tools, and therefore it is not by accident that you see a lot of different things, different technologies that are already introduced by Professor Neugebauer in the machine tool technology. So challenges of machine tool technology. We start with a small introduction to show a little bit the importance of machine tools. Naturally, you see here the biological transformation here. This is, as Raimund pointed out, initiated 2017, at least on the ZIRP in Lugano. And from that time onwards, we also have some collaboration in this field. And where I want to go here, especially in the direction of artificial operator, then the question chatter was also mentioned by Raimund, but what can we do in this field of intelligence against chatter? The question on increase of accuracy in a situation where the costs are increasingly growing due to the fact of the decaying limit benefit when it comes to try to do these machine tool improvements in the normal mechanical way, it is nearly not possible. And then intelligent way against thermal errors, the aspect of self-healing, and I end with a conclusion. So let's start the question on machine tools. This is somehow shows the importance of the machine tool. So every year, machine tools with a value of approximately 60 billion euros are created. 2/3 of them are cutting machines. This is a really important contribution. And that means that we at the moment have a population, a value in machine tools that is existing of 350 billion euro, means that 2.5 million machine tools are running around the world. And for these 2.5 million machine tools, we need to have technology for the future. We need to apply whatever the co-developing enabling technologies provide. And naturally, the population of these CNC machines will also increase by replacing other low technology machine tools in the world. Then
there is something that needs to be taken into account if we look for the productivity and in the direction of efficiency. So approximately 2 to 3% of productivity increase is per year necessary. In the first step, I showed you what was the source of this increase in the past. So we had enhanced tools. We use machine tool architectures and structures that are from the performance better. We have chatter resistance. We have higher power densities in the drives. We have higher cutting speeds, and so on, so on. A lot of different things that enable year by year these 2 to 3% productivity increase. And the question or the result is shown here. So in former times, this is for a grinding machine, it was mainly the grinding time that was reduced. But on the other hand, we must not forget that the auxiliary process time, especially the automation, and there I want to address this directly to Professor Kapitanov, who is expert in the field of automation. Also, the automation plays here a major role. And the question is what happens in the future. So we like to adopt properties of biological systems like big sensor, sensor fusion, cognition, machine learning, and so on. And what we also saw is, and this might be one of the major outcomes of the additive technology, that they show us how fast setup of a product can be made in this technology. But we, on the other hand, directly need to discuss, can we adopt similar technologies for the cutting in this field? So the so-called 5-minute machine, after 5 minutes we want to make the first chip if we have a CAD model, and this is the same that we have for the additive manufacturing technology. After 5 minutes we are ready to start with the production. But if we were able to make the first chip after 5 minutes, milling will be much faster. And the question is, where is the limit between conventional technology and additive manufacturing technology? Where is the break even between efficiency, productivity, costs, and naturally also quality? So then another challenge is the increase of accuracy. So this picture is a fairly famous picture, was created by Taniguchi in 1983. That's why it does not last beyond this time of 2000, was then somehow refurbished to make it easier understandable by our colleague McCune. But it shows that machine tools that happen to be precision machine tools back in the 1930s, in the meantime, are normal machines. And that means that all the machine tool manufacturers are in a steady increase of accuracy, reduction of uncertainties of machine tools, positioning inaccuracies must be reduced. And this slide shows that, and actually the slide I showed before is naturally very important for machine tools, but it's actually deduced from the so-called Moore law of increasing the structure density. Increasing the structure density means that we are capable of creating with less amount of material a denser amount of storage capacity that is shown over there, and that enables us that we are the functionalities per chip can be increased, the structural size of the chip can be decreased, and we are heading towards the situation that the structural size is in the vicinity of an atom. The question is how do we change this increase of structural density? And in the past it was always a question on lasers, on better focusability of lasers and structuring capabilities. And the question is actually, does that come to an end? And the answer of this slide shall be, it does not come to an end. We have quite something of technology before us. So we go in the third dimension and we find new, as pointed out by Professor Neugebauer, we find new possibilities to increase the performance of computers. Also, the energy efficiency was already discussed, and it was for us really difficult to see what is actually the proposal of the academia to reduce the energy utilization. What you see here are two different machines. The red is just the stuff for having the machine running, so the supply of media, supply of media. And this is a high productive turning machine. The red one is actually the media supply, And the red one is the production, the real chip making. The red one here also is the real chip making, and the blue one is the media supply. You see that doing the utmost possible for a machine to be prepared for the future in any case does mean that we have a lot of over expenditure of energy in terms of what we really need. And on the in the end, we find out that it is not a general rule that can be applied to all machine tools. That must be treated point by point. But I want on this slide also point out that energy efficiency and saving of energy and renewable energies is a very important topic. But on the other hand, the Earth is equipped with an amount of materials of different kinds, and when it is used up, it is used up, and then we are incapable of doing anything while energy is supplied by the large power station that we have in the heaven. And then Industry 4.0, I actually do not need to discuss that with you. This is a challenge that comes up, internet technology. And then something that is really interesting that happens in the machine tool technology is that in former times, the control of machine tools, the control of machines was running as forerunners to the development of electronics. In the meantime, it totally changed. And what you see here is that we start to control machine tools with actually consumer products, with smartphones, with tablets, and so on. And the benefit of that is that we are capable of providing for extremely cheap price all the different sensors, actors, and the apps that are provided for the users of actually machine tools. So with this structure of apps, you can easily take the whole world as your development group developing new performance, new programs for the machine tool. So then I go to the biological transformation. When we started this, Raimund, we discussed on actually are biological systems superior to our technological systems. And the truth is there are some aspects where they are much inferior to what we are doing. So there's no horse running with 250 kilometers per hour. And I also do not know a whale that is capable of carrying 16,000 containers over the ocean. So in terms of power, in terms of force, in terms of speed, biological systems are by far inferior to what we are doing technology-wise. The question is, what actually can we inherit from the biology? And this is mainly intelligence, so the possibility of reasoning, strategy development, and so on. Biological systems typically have an abundance of sensors. So we have on a square centimeter of our finger, we have 10 sensors for coldness. The question is, what can we do with that? The exchange of information is we are extremely efficient, even over several thousand kilometers from Zurich to Moscow and also to Munich, respectively Dresden and Chemnitz. Then the question of self-healing, and this is something that we would like to point out later on, because a lot of things that we can inherit from biology are nothing, have no value without this possibility of the self-healing, and then a functional integration. So if we discuss on materials, so for instance, what is the performance of a normal tree trunk in comparison to our fiber-reinforced materials? There, our fiber-reinforced materials are by far stronger than the tree. The interesting thing is to adapt to the environment, so the adaptivity, and naturally the functional integration, that the tree trunk does not only is not only there for load carrying, but also for providing nourishment and providing information to the tree. So these are the 5 topics that we really need to deal with when we discuss on biological systems. And for us, very interesting is the question of what is actually the future workforce of our machine tools. And the problem that we witness in Switzerland, that the amount of skilled people that are able to operate a machine are becoming less and less. And the technology is becoming more and more complicated. And therefore, the vision came biointelligent machines would be operator integrated. So some tasks of the operator, especially the complicated tasks, must be integrated into the machine tools. And then the question is, how can we integrate the capability of an operator in the machine tool? Then we naturally need artificial intelligence. And Raimund, in this place, I completely agree. Machine learning is only part of this artificial intelligence, and most people start and say, okay, we need to have a neural network and then artificial intelligence is done. No. If you want to really make these operator integrated happen, you need to use toolboxes of artificial intelligence, and this starts with an expert system that is based on ontologies, so it's capable of creating out of knowledge that we introduce new knowledge by, for instance, comparing, by plausibility checks, by a lot of rules, by physical models, and this all needs to be integrated in the machine tool. Then I specified this as an example for additive manufacturing. The question is why? Because sitting in a barrel and opening an additional bottle is always something that is nice. So additive manufacturing is a new technology, artificial intelligence is a new technology. Now combine these two. Now, the interesting thing is that this additive manufacturing at the moment is still under development, and we have no CAM tool actually available at the moment that covers the whole story. And therefore, it is useful to integrate the intelligence of an operator directly in a new developing program that is at the moment coming up. And then the question is, what are these people that are dealing with the machine? The interesting thing is that the operator, the skilled operator here, needs to operate the machine, and that means that all his knowledge need to be introduced sometime in the machine tool, but in an unstructured way, and might be an incomplete way. And the question is, what does the machine tool with the artificial intelligence and the expert system, this ontology-based expert system comes into play, that each piece of information is checked against the information that's already available on the machine, and the machine starts to understand, to fill in the open gaps in the landscape of this manufacturing technology. The question is, will that be deteriorated if an apprentice is coming and does some stupid things? Then the question is, does the machine tool recognize that this guy has nothing to say? Yes, we can make a plausibility check. The question, and this is something that is really important, at this place, for instance, ethics comes into play. The question is, in all topics of this biological transformation, ethics becomes a major topic. So then we need to have some monitoring, which you see here on top. We have 3 cycles that the machine tool is capable of learning. It starts with a normal closed loop control. Normal closed loop controls are not artificial intelligence, but they are anyway something like adapting the machine tool. But we have different layers of machine learning that are stacked above these. And it is important to see that this is a technology for individual parts. So it is not useful to teach individual parts. It is useful to make a feature recognition, feature separation, and to teach these individual features that can be reused to make this geometry. So here, fairly swiftly, one possibility of sensors, and this is something also that is bio-inspired. We have eyes, we can look and have the possibilities to recognize colors, to recognize the full field of what's happening there. And this is especially optics and acoustics are sensors that are really, really capable in biological systems. That's why the higher biological systems are equipped with that. Then the question is what happens to other machine tools. So grinding is also something where CAM tools are not really existing today. So each manufacturer builds his own CAM tool. And this is a picture that a colleague in Switzerland created once with the performance of or the power of United Grinding Company. They asked 74 experts in grinding to solve manufacturing tasks. So the task was to make 3 different cylinders and to provide the roughness for these cylinders. And the question is, were these experts actually available in the first step to fulfill the task? And you see the fulfillment of these now 6 different features that need to be done are covered in the green. So if the green is coming here up, then this guy fulfilled every task of these 6 things, and the farther it is away, so this one achieved nothing. So, and the question is, what happens then? And this is a typical way of setting up machine grinding operations. Then there's an iteration, so you start to redo it, to make a new approach, and in the end you find the situation. This is the first interesting thing, that these experts need iteration. The second interesting thing is that in terms of a fairly crude and expert system, we are capable to be better than most of the experts. So only 11 experts in this term were better. And that means that an expert system is something that's really valuable in terms of increasing the productivity, in terms naturally also on reducing the energy expenditure, because during this time where this machine tool is set up, you need to supply the energy to the machine tool. And the last thing is that we can do it better as humans than this expert system. So the learning ability of the expert system is something that is really important. And with this slide, I want to point out that's exactly the same structure that we use. I also want to point out that the approach keep it simple is a completely stupid thing, because keep it simple means we have the problem with keep it simple is we have to cope with the full complexity of a manufacturing process. And manufacturing processes are complex. And therefore, if you want to interpret this slogan keep it simple correctly, it must be keep it simple towards the operator, but then the machine tool needs to fulfill all the problems that coming up from the complexity, which is actually the task of having persons or having the operator integrated. Okay, so then sensors in abundance. When I started discussing on temperature compensation of thermal errors on machine tools, and I asked the Swiss machine tool maker, I would like to have an additional thermal sensor, temperature measurement sensor on the machine tool. They said, no way. The sensor is an additional component that first costs money and second increases the downtime of the machine, so we shall not do it. In the meantime, some 6 years elapsed since that time, and you see that even large machine tool makers, they make advertisement with a large amount of those temperature sensors to really gain control over the capability of over the performance of the machine. And it is interesting to see that in the meantime, we learned that, for instance, sensor fusion is something that's interesting. We combine the information that are coming out of different sensors, and we are also capable of making plausibility checks. So if one of these different temperature sensors fails, then the other ones can check, is it plausible what happens there, and then mute the sensor, as we are doing day by day with the sensors that we have at hand. So then the question, what about chatter? What has chatter to do with the performance increase due to, for instance, artificial intelligence? I only want to show you with this slide what actually is the goal. So we achieve, if we, first let's look at this picture that shows shattering is a self-excited vibration. So the machine, out of its own turning of the tool, generates vibrations, and they're becoming stronger and stronger until non-linearity takes place. And non-linearity in machine tools typically means the crack of something. And therefore, it is necessary to avoid chatter by any means, but it is also visible that at different parameters, the productivity can be increased by more than 1,000%. So if we can exploit this chatter, we would be the kings in terms of productivity. Then the question, chatter happens at different places in a different way. So the goal is updating the stability prediction by monitoring stability states of regular cutting operations. So the machine is cutting at different places, and naturally the stability is different at these different places. And then the question is, we measure at one place, we measure at another place, we measure at a third place. Then we ask ourselves, what is actually the updated prediction? And in the end, we find perhaps something where all the chattering points are sitting outside of the line and the non-chattering below. And then we achieved actually the possibility that we can exploit the gaps between these stability lobes where we achieve a higher stability. The problem is that these lobes are changing very fast, and they are changing without somehow knowledge of a human person. And the topic is that chattering in machine tools is one of the most researched topics in manufacturing at all, but there's no industrial solution available still. So the question is, what shall we do? So now the savior of all our problems, all our technical problems is coming up. That is artificial intelligence, so self-learning technologies. We have actually two possibilities to deal with the problem. We have this analytical topic with modeling, physical modeling. Then the problem is that we have low prediction accuracy. On the other hand, we can use a data-driven model. This requires unaffordable demand of experimental data. So the solution would be something in between. So to solve the benefits of both of them, combine a model with a database optimization, and then in the end we will be capable of adapting this stability lobe diagram from whatever the machine witnesses. And then we see that it is necessary to teach these models as an artificial topic. But on the other hand, we have besides this network, we have model inputs, and out of these model inputs, we generate a stability model. This enables us to predict. And then we compare our experimental data. Does it chatter? Does it not chatter? So we need the sensor on top and compare it, and then reorganize or retune our network weights. And what the problem here is that we cannot exploit each and every experiment because of the problem that we have something like a digital situation that needs to be learned. So either it chatters or it chatters not. So if you predict chatter and it chatters, then you have gained nothing, and you only gain something if you have a contradiction between these two models. And then there's coming up the problem, machine tools are changing on purpose. So we want to exchange the tool, we want to exchange the clamping situation, and that means that in the end we end up with a lot of different models that need to be tuned and give in the end a stability model on terms of a physical combination of these different models. So physical combination of these models is something that is essential to win over the variety of these different equipments of machine tools. And then the question is, can we enhance that? Yes, we can enhance that. So what we at the moment propose, and this is a collaboration with an industry partner, with a control manufacturer, we propose this Ensemble deep learning. That means that we start with a lot of learning of neural networks. We try to start from different starting points. We gain different results. So the first thing is the original predictions that you see here, analytical model prediction. Then we have the training of the network with these different points. In the end, we end in real individual predictions for any different setup of this artificial intelligence network, and the goal is to make to have then the averaging out of these different events, out of these different trained networks. And then the question is, does that really help? Yes, it does help. The green is the non-chattering, the red is the chattering part, and it is clearly separated by the black line. So then compensation. The question is, how do we compensate machine tools? The necessity is to rethink the machine tool at this point, because you can only compensate what is predictable. And then if we ask for design for compensation, the first task is to have repeatability. The second task is to have repeatability. The third task is to have repeatability. So there is nothing that goes over repeatability. Only if it is repeatable, and this is what we need to achieve. If the machine tool is repeatable, we gain possibilities to enhance by compensation. And then the question is what all can be compensated. So we can compensate kinematics, gravity, dynamics, thermal behavior, wear status. This shows the dynamic compensation with the compensation of these crosstalk and intalks coming from the distance between the center of gravity and the attack point of the drives. This can be actually predicted, and this is something that is deterministic and and repeatable and can be used for enhancing the accuracy of the machine tool. So the problem of enhancement of machine tools, model-based enhancement of machine tools, is that we typically have models that are by far too complex to be evaluated on due time. And therefore, it is necessary to have advanced models and meta-modeling. And this is the task that we look for in each and any compensation strategy that we have. And I only want to show you some possibility of dealing with the thermal compensation. So in old times, the so-called resource-based technology, we ask for air conditioning of the job shop where we put our machine tool. In the new time, we want to have a machine tool that makes ultra precision or is capable of ultra precision but operates in the standard environment to save energy. And therefore, the only possibility is to be a little bit more intelligent, to be a little bit more prudent, have models, know how the machine will behave, and then set up physical models. But the question is, are these physical models sufficient? And here I show you something like any compensation strategy works. This is something like a morphological box. We start with a sensor technology, and excuse me that I have the NC program also as a sensor, because from the NC program we know how the machine tool needs to behave. Then we have the intelligence between the model, and we have an actuator technology, and this should be the axis of the machine as far as possible. And perhaps also might be some additional access, but we prefer to have the same actuators that we actually would like to have. And here you see physical field equations that require a lot of evaluation, and therefore it is interesting to go in the direction of reduced models that have a reduced information content in comparison to the physical model, but then we need to install something different to be capable of enhancing this model. So we ask for different sensor technologies and then put it into some reduced modeling. And I show you this phenomenological modeling in a few seconds. And therefore, the question is what can be enhanced to make this phenomenological model work. So the question is, how does a phenomenological model work? So we have a physical equation. This physical equation is complicated. We reduce it to a simple first-order differential equation. This contains at least the history out of this compensation technology, and all the parameters here need to be adjusted by parameter identification. So we ask for movement of the machine tool. We ask for the deviations of the axis positions. Then we make a parameter identification. If we have done it well, we have a very good comparison between those two different things. And then we take another one, ask for using the same prediction, and in the end ask for the measuring and look whether it happens or it happens not. So you see that we have approximately 80 hours. Machine tool that lasts or that works for 80 hours is nothing. So what we need to do is we need to retrain this model such that the parameters that we identified become somehow adapted to the situation of the machine tool. And this is how we do that. So this is actually the utilization of the model after the training. Then from time to time, we measure the position of the machine tool. After measuring the position of the machine tool, we feed back this information that we got into our model, and then we have a new model, and this actually lasts forever. No? So let me skip some of the slides, otherwise you get nervous. The last thing that I want to show you is actually the question of the self-healing topic. So here we generated some surfaces that are functional surfaces. Functional surfaces are known from lotus leaf and all that stuff, that is super hydrophobic behavior of the machine tool. But you know, when you touch the surface of a lotus leaf, the super hydrophobicity is gone. And the only thing why this plant survives despite this touching is that it is capable of regrowing this surface, the performance of the surface. And therefore, when we discuss on functionality, we definitely need to discuss on the regrowing, on the self-healing topic. And I want to show you one aspect of self-healing. This is a beaver. The beaver has teeth that are sharpening themselves. If the beaver does not cut wood, the teeth are growing ad infinitum until the poor animal dies. And this is something that is actually interesting for machine tools. We would like to have machine tools in the machine tool that are self-sharpening, that keep the sharpness due to the wear process. The problem is only that we cannot grow the material from which the tools are done, but what we can do is we can move the CNC, so the axis, so that the length of the tool appears longer after some time. So, and this is what can be achieved. This is drilling of carbon fiber reinforced materials. You see here the behavior of the cutting edge. The behavior of the cutting edge was originally like this from two different tools. And due to the effect that we created from coating and from the geometry of this machine tools, you see that the cutting edge becomes sharper, and that it can clearly be seen that the uncut fibers are becoming less and less. The problem is only that we start with a bad fiber in the beginning, because this is what we have ground. So the question is, can we enhance this also, for instance, by introducing laser sharpening of these cutting tools, which is done at our institute. Let me come to the conclusion. All these artificial intelligence topics are somehow here in this so-called Gartner hype cycle in this area. So they are all dropping down in the trough of disillusionment. We had that for artificial intelligence some time ago. That was the so-called artificial intelligence winter. And the question is, what are we as researchers doing? We need to act in this situation, because here we are capable of bringing things into the industry. And so I come to the conclusion. The important thing is that we use the involving enabling technologies. Naturally, the machining systems become compensated, they become intelligent, and they naturally become bio-inspired. I want to show you that compensation for accuracy is something that is necessary to be done. And we need to have models. These models become more and more complicated, and that means that we have to introduce these artificial intelligence topics. Thank you for your kind attention.
Thank you very much, Professor Wegener, for a very interesting report. And we can imagine that you've done a lot in your institute, but it's really very, very interesting. And I think that's maybe we shall invite you for our students to make a lecture or 2 lectures in this field. Okay.
As an honorary doctor of this institution, I'm obliged
yes.
to do that.
Honorary doctor should a little bit work for our university too. Well, colleagues, we are going on, and I would like to introduce our Russian speaker. We have a very good relations with our industry and with our companies. And firstly, I would like to introduce Mr. Bakhin. And Евгений Викторович, только если можно покороче, у нас уже мы выбиваемся из этого самого, а так как вы будете на русском, придется еще чуть-чуть переводить. Хорошо? Thank you very much. I ask him to be not so long, because it's necessary a little bit translate, because he'll speak in Russian. And okay, please.
Да. Добрый день. Спасибо большое, коллеги. Исчерпывающие, великолепные доклады наших гостей, за что им отдельное спасибо. Поэтому я сосредоточусь не на трендах технических и технологических, а больше на трендах цифровизации, ну, как профильная компания, и на взаимодействии в связках институты, IT-компании и промышленный бизнес.
Hello. Welcome, colleagues. Today I would like to talk with you not about manufacturing, but more about the digital transformation and topics regarding that.
Прежде всего, я могу сказать на нашем огромном опыте работы с отраслями индустрии Российской Федерации, Евразес и дальнего зарубежья, что любая технология является следствием объема рынка, что, собственно, и было показано очень наглядно в докладах наших коллег. Драйвером инноваций и технологий является размер спроса и потребления продукции.
Based on our industrial experience, I can say that the main driver of the market, the main driver is the size of the market.
Поэтому ключевым вызовом на ближайшие годы для российской промышленности, неважно в какой форме собственности, в государственной или в частной, для российских цифровых компаний, для нашего сотрудничества с зарубежными коллегами является тот размер производства в стратегических отраслях, в том числе в станкостроении, который будет в соответствии со стратегиями промышленности, которые были утверждены в прошлом году Минпромторгом и председателем правительства.
So the key for us and for our industrial colleagues is, as we mentioned, the size of the market, and especially what was indicated by our government for us, and that is the main orient for us to develop.
Если опустить сейчас акцент на технологиях, опустить акцент на деньгах, которые нужны для того, чтобы создавать новые предприятия и модернизировать имеющиеся, о чем скажет отдельно мой коллега из промышленности, из группы СТАН. Важнейшим элементом той системы, которую нужно восстановить и развивать в Российской Федерации, являются хорошо обученные, подготовленные кадры, цифровые инженеры, которым предстоит работать в 20-е и 30-е годы.
Despite all the accent which we placed already, economical accent, we think that one of the main things is actually the education for our people and to the people who would be actually available on the market by 2030.
В данном контексте как никогда велика роль станкина.
At this context, the main role is on the станкин.
И именно станкин будет руководящим звеном в подготовке инженерных кадров, в том числе цифровых инженеров для работы в станкоинструментальной промышленности России.
And Stankin will play a key role on preparing those people, especially in the direction of machine tools and manufacturing.
И на примере связок успешной подготовки инженерных кадров в ряде других отраслей я могу дать несколько рекомендаций и практический пример.
I can do several organizations based on our experience, industrial experience.
Одним из очень крупных наших заказчиков в радиоэлектронной промышленности, входящим в Ростех, является красноярское предприятие «Радиосвязь».
One of the biggest customers of us is the Krasnoyarsky factory of radio electronics.
Там же в Красноярске профильный вуз Сибирский федеральный университет.
They are located at Siberian Federal University.
И модель подготовки новых кадров, она, в общем-то, достаточно простая и очень эффективная. Это единое цифровое пространство предприятия.
Digital environment.
Это единое цеховое пространство. Нету различий между лабораториями и опытными площадками в университете и цехами предприятия. Это одно и то же.
This is a joint digital space which merge together the laboratories in the university and the factory.
Это единое пространство задач и производственных потребностей. Студенты, начиная со второго курса, решают не отвлеченные задачи, которые им придумали преподаватели, они решают практические задачи непосредственно в цехах и в КБ предприятия.
It's a joint task which merge together the university and the factories, as we mentioned before, and especially what is interesting that the students already starting from the second year learning not what the teacher has prepared, but the real cases on the factory.
Соответственно, нет никакого зазора, никакого разрыва между задачами, которые поступают на вход по новой продукции или по улучшению качества на предприятии, и решение этих задач в учебном процессе. Это одно и то же, отставание нулевое.
So they fill this gap between the university and the industry, and then we can prepare workers without any delay in knowledge to the state of the art.
И мы уверены, что как бы совместно работая со Станкином и силами нашей компании, как цифрового игрока и разработчика IT-систем, и компаний отрасли, таких прежде всего, как группа Стан и Балтийская промышленная компания, которые сейчас лидеры в станкоинструментальной отрасли России, и привлекая лучший опыт зарубежных партнеров, эта система будет очень успешно оттиражирована в Станкине для подготовки нового поколения цифровых инженеров для российской промышленности. Спасибо.
And we are sure that using the industrial experience from our company, using the experience of Stan Group, of the Baltic Industrial Group, we integrate all this knowledge in Stankin University and have a success at the end. Thank you.
Thank you very much, Mr. Bachin. I not introduce, he is a member of board of our very famous soft company. They produced CAD systems and CAM systems and CAPP and were, I think, the biggest in our market in this field. And now I would like to invite Professor Kapitanov and Mr. Bachin for signing agreement memorandum of understanding between Stankin and Ascon company in the field of education and research. Please.
Табличку, пожалуйста.
Теперь я от Швейцарии буду подписывать.
Professor Kapitanov a little bit joked that just now he signed from the side of Switzerland. Thank you very much, gentlemen. Yes, and we are going on due to our program. And okay. And now I would like to introduce Mr. Zvyagintsov. He is a managing director of our biggest machine tool company. And our good friend, and that's why I'm very happy to see you here. Please.
Добрый день, уважаемые коллеги. Спасибо большое за возможность услышать прекрасные доклады. Особенно мне, как человеку из промышленности, понравился доклад уважаемого господина Вегенера. Мне это все очень близко.
Thank you, colleagues, and as a man from which represents here the industry, I especially loved today keynote speakers and Professor Wegener and Professor Neugebauer.
Еще раз спасибо, и хотел бы коротко рассказать о сегодняшних проблемах российского станкостроения.
So, excuse me. Thank you. So today I speak about the main challenges of Russian industry.
За последние 10-20 лет масштабы российского станкостроения сократились значительно.
In last 20 years, the market size of Russian manufacturers has reduced dramatically.
Как в количестве предприятий, так и в количестве сотрудников, которые на этих предприятиях работают.
Both the number of companies and the number of employees in the factories.
Как и следовало ожидать при переходе с плановой экономики на рыночную, невидимая рука рынка сделала свое дело.
As it could be expected that with a change from the plain economy to the market economy, the market hand has made its deal.
Ряд компетенций в отрасли станкостроения существенно был ослаблен. В частности, это коснулось зубообработки, изготовления кузнечно-прессового оборудования, электроэрозии, электрохимии и ряда других.
So it especially touched the manufacturing in the fields of electrical erosion, the gear teeth cutting machines, and stamping.
Но в то же время наиболее востребованные направления металлообработки в станкостроении сохранились, развились и совершенствуются.
But the most important parts of the manufacturing remained, and it's developing, and they are developing.
В токарной обработке мы видим сегодня предложения российских станкостроителей ничуть не уступают лучшим иностранным образцам.
We see that in turning, the machines produced in Russia are not worse in all cases than the machines produced by other countries.
В российских системах учета российских производителей, имеющих подтверждение Минпромторга, появляются производители, изготавливающие станки по классу А.
We do have the precision machines present on the market based on our Ministry of Trade and Production Research.
Заводы по производству фрезерного оборудования осваивают различные высокоточные машины для пятиосевой обработки.
Our factories which produced milling machines are now capable of producing high-precision 5-axis machines.
Заводы, которые производят станки для круглой шлифовки, предлагают ультрапрецизионное оборудование.
The factories which are producing grinding machines now is capable of producing ultra-precision machines.
Производители, в том числе находящиеся в структуре группы СТАН, изготавливающие профили шлифовальное оборудование, прочно обосновались в нише прецизионного оборудования.
Also, the machines produced by our companies, which are included in the STAN group, are capable of producing high-precision machines.
К сожалению, для наших западных коллег серьезно потеснили их на этом рынке.
And despite of the sad feeling of our international colleagues, the part which we are producing is constantly growing.
Большинство из упомянутых мной видов оборудования производится серийно.
The most of the equipment which I mentioned is a series production.
На проходившей выставке на прошлой неделе «Металлообработка 2021» все это можно было увидеть воочию.
In the exhibition which just ended, Metalloobработка 2021, you could have a chance to see all these machines in real.
Особенно было интересно наблюдать за бурным развитием технологий с применением лазера.
Especially it's interesting, or it was interesting, the laser machine we presented there.
Порадовало сообщение от одного из разработчиков, с которым мы давно знакомы, о том, что лицензию на изготовление его оборудования приобрели восточные коллеги.
It was very pleasant for me to hear from one of my colleagues that the license to his equipment was bought by our East colleagues.
И нынешняя ситуация, несмотря на все сложности, показывает, что у российских станкостроителей есть какой-то секрет.
And despite of all the challenges which I mentioned and which we see now, it shows that Russian manufacturers have its own secret.
Я его вам открою.
And now I tell you what it is.
За последние 20 лет наши заказчики привыкли к оборудованию, которое им поставляли лучшие мировые производители.
In last 20 years, our customers used to have the equipment from the best machine tools companies of the world.
Наши заказчики при формировании технических заданий не стеснялись последние 20 лет устанавливать самые высокие планки.
Our customers in last 20 years was putting the highest possible level for the required equipment.
И я неоднократно был свидетелем, когда наши конструктора, технологи, смотря на очередную задачу, спрашивали, сколько можно модифицировать имеющиеся модели под то, чтобы повторить очередной шедевр иностранного станкостроения.
And I was told many times by my engineering colleagues that they are asking me how many times should we repeat or reverse engineering the masterpieces of our other country colleagues.
Прошу поправить, не реверс-инжиниринг, а самим создать продукцию, отвечающую тем же самым характеристикам, к сожалению, без реверс-инжиниринга, своими силами.
Excuse me, I have translated wrong. It is not a reverse engineering. It is a creation of our own products, which is at the same level of the products from our competitors.
То есть я хотел выразить огромную благодарность нашим мировым коллегам, лучшим производителям станков за то, что наши производственники, наши конструктора, технологи натренировались на лучших образцах иностранной техники.
And here I want to say thank you to my international colleagues from the abroad that our factories and our engineers was trained with such great masterpieces of machine tools over these years.
Но, к сожалению, у этого подхода есть и недостатки.
But there are some drawbacks on going this way.
Это достаточно высокая себестоимость.
It's a high price, high cost.
High cost. И наличие так называемых детских болезней у новых моделей оборудования.
And also some child mistakes of the equipment which is just created.
Но к нашей радости правительство России поддерживает нас в части экономики, соответственно, мы можем компенсировать себе различные проблемы с себестоимостью.
But to our luck, we receive some compensation from the state. Submission.
А наши заказчики толерантно относятся к проблемам. И в режиме постоянного взаимодействия мы исправляем те ошибки, которые могут появляться, когда мы создаем новую технику.
And our customers tolerate all the programs which we have during the creation of the new machine tools.
И как раз вот здесь крайне эффективным могло бы быть взаимодействие с станкином, со структурами станкина, если бы у нас появилась эффективная система по принципу, построенному в фраунхоферовском обществе.
And especially here, I see that there is a huge potential in collaboration with Stankin, especially if we build this collaboration based on the experience of the Fraunhofer Society.
С огромной радостью наши станкостроители бы обращались за экспертизой сделанных решений в части расчета прочностных характеристик, динамических расчетах, тепловых расчетах, расчет компенсации вибрации.
With a great pleasure, our constructors would refer to the experience on our colleagues from the university regarding thermal modeling, compensations, dynamic compensations.
Как мы знаем, для этого требуется высокопроизводительное оборудование, дорогостоящее программное обеспечение и богатый опыт.
As we know, for that we need expensive, high-performance machines and also very software and huge experience.
Потребителями могли быть как большие заводы, так и молодые начинающие стартапы в области станкостроения.
Customers could be as well as big customers and also startups in the manufacturing field.
Также, я не знаю, насколько это будет инновацией, но было бы интересно получать помощь в вопросах расчетов и оптимизации производственных процессов и, как следствие, себестоимости.
It would be also very beneficial to receive help in the compensation and in the calculations of costs.
Экспертиза в области применяемых решений с точки зрения комплектующих изделий.
Expertise regarding machine parts.
Таким образом, можно было быстро сохранять и расширять имеющиеся модельные ряды.
So we could keep and extend our production models.
Повышать качество и уменьшать стоимость.
Increase the quality and reduce the price.
Есть много идей, витающих в воздухе, которые можно было бы реализовать во взаимодействии между российскими станкостроителями и Станкином как флагманом нашей машиностроительной и станкостроительной науки.
There are multiple ideas flying around in the air regarding what we can do together between manufacturing companies and Stankin University.
Но начав с этих маленьких задач, которые я сейчас обозначил, можно было перейти к более масштабным.
But starting from the bullet points which I have just mentioned, we can go to more to the bigger tasks.
Спасибо.
Thank you very much.
Руслан Валерьевич, большое спасибо. Thank you very much, Mr. Zvegentsov, for your kind words about our cooperation and about Stankin. And now I would like to introduce Mr. Akhatov. He is the director of the Center of Additive Technologies of Skoltech. It's from Skolkovo, and we are glad to listen to him. And this is our last keynote speaker. He's last hour. Okay.
Well, thank you, Mr. Chairman. It's a great pleasure to be here. So, first of all, it's a great day for Stankin, and I'd like to take advantage of my podium here, so to convey my congratulations and greetings from all leadership and students and staff of Skolkovo Institute of Science and Technology to you all. This is a great day, and I'm honored to be here and represent Skoltech. So first of all, what is Skoltech? You see these two beautiful pictures. This is probably computer vision. In reality, it's not as shiny, but still good. So that's how it looked like. It's a brand new campus built in Moscow. And I'd like to do some geographical introduction to you. So this is a map of Moscow, specifically for our international guests. You will see that this is a red square over there on the west side of Moscow. That's where Skolkovo Innovation Center is located, and the entire campus is placed over there. And that's how it looks from the top. And this is the entire area of Skolkovo Innovation Center, and the campus is a ring building, big one, on the upper right side. So I take an opportunity to invite everyone and our international guests to visit us sometime when it is possible. Now, I'd like to start my presentation, which is entitled Multi-Scale Materials and Technologies. I just would like to underline multi-scale materials and multi-scale technologies both. This will be a kind of a snapshot of several projects and directions that we're actually doing in Skoltech without pretending to cover the entire area, which is huge, obviously. I will be talking first on conventional scales technologies that are additive manufacturing, that are composite materials production, and that are functional coatings. And after that, I will do several examples of microscale and nanoscale technology, which we are also doing, which is not very relevant for our meeting today, but still just to show that we have them. So first, I would like to I apologize, the screen is going up. So first, on additive manufacturing. It has been already presented today extensively, and in this audience, probably everybody was familiar with this. However, the major feature of this additive manufacturing is we are not just doing a product by additive manufacturing, we're also simultaneously generating new material, both. So material and product. Therefore, studies on additive manufacturing, it's a part of material science, part of mechanical engineering. It is a combination. And we in Skoltech do, in this regard, also study different mixtures of powders. Well, there is no much of scientific background how to mix powders and what to expect when you will be getting. Unfortunately, it's like a turbulence. It's a problem forever. You can study and spend all your life trying to understand in depth the physics behind it. And that's what normally people do. We start doing this high entropy alloys, which is basically abbreviation for simple mixture of several materials together in about the same proportion of mass. And here it is shown additively manufactured alloys, which will basically study structure. And you see, it is shown that depending on direction, the domains are basically oriented in a very specific way. And the most importantly, the temperature dependency, because these high entropy alloys are good candidates for high temperature applications. And you see on the graph on the right, when temperature rise, the tensile strength or yield strength is reducing. However, the quality of yield strength, the amount of this, is still higher than hot rolled products. So if we do additive manufacturing, surprisingly, we are getting a higher yield strength materials. And this is something to be studied, and that's what we are doing, trying to compare as-built and annealed products. I just would like to underline, since there is no physical background on that, it's a lot of done in the labs by experimentation. After that, what we do normally, we try to put it in the high pressure torsion or whatever else aggressively squeezing this material, and it shows that actually the prehistory done by additive manufacturing is dying because of this. All this domain structure is being ruined in the same way as it would be ruined if it would be casted. At the very end, you see the horizontal line, the limit, is achieved as the same in terms of micro hardness. So the material is forgetting the prehistory, how it was created, which is also important to learn and understand the consequences, what actually we are doing. Obviously, being university, we're always publishing and publishing and publishing, and everybody in this room know that, and I just would like to show we also do that. And the second branch of our activity is additive manufacturing of technical ceramics. This is something absolutely unknown. Well, what we do, the list of these ceramic materials is covered by this high-tech device. But this is aluminum oxide, zirconium, and all kinds of ceramics. And here shown samples that basically we made in our lab. In order to present what actually we are doing, so this is a whole line of additive manufacturing for ceramics made by SLA technology. That's what we do in our lab. We have this Keramaker 900, and our engineers and staff learn how to use it already since several years. This is a piece of art, of course, how to do it, and that's exactly resonating with your item that you mentioned, that it is kind of a qualified operator supposed to be attached together with this machine. So it doesn't work like you push button, you get the result. But after this learning, we found that it's important to find how structure of these materials change, and we basically do this all, including mathematical model of all these processes, like digital twins of all these 3 steps: predictive numerical model for 3D printing, predictive numerical model for thermal debinding, and for sintering. There are several different time scales of these processes, and we develop all these models for that to be able to predict final product before it is printed. Now, the second step in this direction, we also do 3D printing piezo ceramics. This is a very different material, and it requires for processing a different wavelengths of lasers. Therefore, we had to generate or create our tabletop laser ourselves in Skoltek, which is shown on this actual photo picture, and this is made in Skoltek. And the samples of our printed piezo ceramics is shown on this picture. Is just the first examples that being now exhaustively studied in our mechanical testing labs in the Skoltek to understand how to select a better technological regimes for these printers, and obviously published in Ceramics International. Now, the third one in additive manufacturing, which was well mentioned today, it's very poetic application of additive manufacturing. We print with a lunar regolith. This is interesting. Someone say, well, why do we care about that? Well, like everybody is dreaming now, we would like to fly to the moon one day, maybe our kids, maybe our grandkids. And in that moment, we would like them to know how to use the material which they find on the moon. And it is possible to print with regolith. It is shown here, and on the picture you see microscopy pictures of the products that has been done, which is kind of mimicking biological implants just for fun. We didn't pretend to do biological implants from lunar regolith, but it was just something to print. And obviously, once we started this, we've published a very exhaustive review on this subject in Acta Astronautica. Now, second point, what I wanted to mention, now, having all these tools on additive manufacturing, we found a little bottleneck in the development of this technology. This is in the software. So when you normally use 3D printing, you use a standard software to process 3-dimensional images to be able to do this printing. Now, if you would like to change the design, normally it takes a lot of time for skillful people to sit in front of computer and redo 3-dimensional design. For skillful people, it is possible. However, it takes a lot of time. At the moment when you decide to print a fractal structure, very sophisticated, with a lot of pores, with different scales of pores, then it's getting really bottleneck. What we suggest to do, in which direction to go, we develop a different mathematical approach in our group, and this is called functional representation for 3D modeling. So instead of representing 3-dimensional picture with a so-called finite element approach and so on and so forth, we basically suggest to use formulas for that. So a 3-dimensional object is being created as a program. You click on this, and all formulas creating 3-dimensional object. And it is shown here that there is special mathematics on that. If you consider a cube and subtract square or sphere, then you're getting something like this. So on the formula language, it is called functional representation. So we've developed this software, actively incorporated in our 3D printing platform. And what I would like to show you now is a little movie how this works. Now you see, this is a shape deformation on the left corner. Instead of cube, you're getting torus. And by changing just parameters in a real-time scale, you don't need spend time, you don't need skillful people, because all these parameters are collected as joysticks on the right upper corner. Oh, it's going too fast, but it's okay. This is implants printed, and this is some porous media that we have done for catalysis purposes, like catalytic media, with a pre-designed porous structure, which is impossible to do by regular means, but by functional representation, it is done very easy, the way you see it on the screen. Now, and a simple example of a hip joint, and you saw all this, right? If you want to add there a very sophisticated porous structure around, because for biological implants it's very important to have it, to have a biocompatibility with the muscles, with the tissue and all this. So this can be done just on the level of sitting in front of computer and typing. So this, in combination with all the tools of additive manufacturing, can be used as a platform for biological implants. Now, next direction, what I want to share with you, it's a composite materials. So there are many of them, and we normally focused on the polymeric-based composite materials, but even though we selected a special one technology, it is thermoplastic pultrusion. So this schematics of pultrusion is shown on this scheme. You have a lot of fibers stacked together with the resin, and after that they go through the preheating furnace over there and goes to the cooling die, and after that, with a pulling of 6-ton power, you're pulling out a special product which is shown on the right upper corner. Like you can make it 24/7, so it's going to be long, and you can make any shape. And what we do, we basically do simulation of this technology to predict the property of final products. This is a very interesting tool for civil engineering. And one of the applications I show here, that's what our innovation in Skoltech. You know, in Skolkovo we all dream about innovations, right? And this is one of the simple innovations. We simply suggested to replace metallic bar from these windows by composite bar. And the advantage is clear. Metallic bar is very thermally conductive. It doesn't save heat. And composite stuff will prevent heat transfer, and therefore it is very advantageous. We basically already got 3 patents on material, on technology, and the product, and now we are kind of doing a test series of these windows to put it on the display somewhere and to make industrial justification that this is a plausible technology. A third direction is functional coatings. So in Skoltech, we have all kinds of thermal spraying techniques installed. And here I just show only one, which is called cold spray. So the application of this technology can be any. So there are many of them. But we decided to apply it for special purposes. You know that from the physics, if you take 2 conductive materials and stick them together to make a contact, due to roughness and due to oxide films between, the resistance of this contact will be very high. Therefore, heat losses due to this resistance are rising. Energy is being lost. And if these contacts are many, like on a power station, or substation, or whatever, where hundreds of them or thousands of these contacts, then these losses may become detrimental to kill the economy of the enterprise. Now, what we suggested is the following. If you use cold spray on the surface of the material, of the conductive material, then it would be nice to disturb the surface in the way it is shown on this cartoon. Why? Because by these hooks, it will basically increase stability of the contact. It would be much more difficult to rip it off. And we reached the level of adhesion strength above 90 megapascal, which is very good. And that was achieved when we basically use cold spraying of copper on the conductive material. And this was patented here, and now we are basically exploring the possibility of using this for bus bar joints at metal production by electrolysis. There are many of them at DC transformer and substations and high current transmission lines. So this is a kind of one of the plausible applications of cold spraying technology. Now, in general, about innovation strategy of Skoltech, I like triangles. So, well, probably many people do. So this triangle demonstrates the correlation between basic research. We all learned how to do it in universities, right? After that, you publish your research and go to technology development, but this is a background. After that, in order to bring it to society, you're supposed to do technology transfer to this mountain. And this mountain is very high. It is called certification of materials and technologies. We learned in Skoltech that this is as difficult as basic research we do. And that's why this is a triangle with the same angles. So they are all equally important. And what we do in Skoltech is presented here. This is a virtual testing for certification. There is a big program funded by National Technology Initiative in which we develop a digital platform for certification. The ideology of this is straightforward. I don't want to talk long about this. It's actually some of the tests can be replaced by digital simulation. And this could be done only if these digital twins are verified, justified, proven, and so on and so forth. However, all this has to be done together with governmental structures. What we do, we work together with, in Russian it is Morской Register, or Maritime Register, and we work also with United Nations Economic Commission for Europe and for International Maritime Organization. And our representatives are basically included in working groups in Geneva where they discuss international rules of certification of composite materials for tanks. Now, that's how it works. And this to show some equations just to demonstrate that we do know equations. So they're presented here. So, and we do mimic this physics of these tanks, of the valves and all this stuff digitally. And this goes to the regulatory documents. And on the lower right corner, it is shown the international note written by our administration to Geneva, and this is being discussed over there in a very specific case of safety of transportation with composite tanks to transport hazardous materials. Now I am just moving to micro technologies, just an example. So sometimes technologies are getting smaller. So you deal with the very small pieces of materials. And even in additive manufacturing, it is possible. We don't do it yet. But here I show so-called direct write technology. And you have a nozzle or capillary, and through this capillary, you have an aerosol flow. And this aerosol needs to be deposited on the substrate, making a very thin line of 10 micron or 15 micron thickness. It's for microelectronics. And just to show you that it could be done, let me show you. Yeah. That's how it is on movie. That's how aerosol particles are flying. And if you see the bar on the scale, the thickness of this beam is maybe 30 microns. And this is flying down to the substrate. And now on the substrate, these aerosol particles are smashing to the substrate, evaporates, and nanoparticles of ink stick to the substrate. And if this ink is made of gold or aluminum, they make a conductive wires. This is a possibility. Obviously, a lot of physics are involved, and in fact, this microcapillary aerosol flow is driven by very sophisticated system of forces. One of them are shown here, which is in direction perpendicular to the flowing particles. Now, nanoscale technology. This is already nanofabrication from nanosize to micron range. And here it is shown our clean room where we do integrated circuits and various applications. In this particular case, this is a modulators that basically modulate terahertz technologies. And these groups are working together with other people in Skoltech who do 5G project. In fact, the entire territory of Skolkovo Innovation Center are covered by 5G now. In our campus, there is a Wi-Fi 5G. So if you come visit, just don't hesitate to click on it and you will get it and you will try. It is on trial mode, but of course it is in a collaboration with the Russian telecom companies, MTS, I forgot already the abbreviation of them. And that's how the technology is coming down to communications once scale is going down. Obviously, it is all associated with the high performance 3D modeling of all these phenomena in nanostructures. One interesting example of nanoscale technologies, the phenomena is graphene nanobubbles. Everybody heard about graphene after Nobel Prize, right? So, and this is a Russian guy who basically got it, and from his group, the picture is taken over there. These little rings, it's a nanobubbles on a graphene sheet. Now, how can you imagine, if you ever buy iPhone and go to the store just to cover it with a protective film, have you ever tried it? You will never get it flat. There will be always something like this on the surface. And you will spend half an hour after that squeezing this. So due to some imperfectness, they are over there. The same happens with the graphene on nanoscale. If you take a stack of graphene and put single molecule graphene layer on top, you will get all this. And schematically is shown that something inside, nobody knows what is it, obviously, because the footprint is 100 nanometers. You can test it with the atomic force microscope and so on and so forth. But interesting, what we've done molecular modeling assuming that there's some argon molecules in there. Nothing special. They're playing around. However, you see, these all crystallized. They made a perfect crystalline structure. Temperature is higher than crystalline temperature. At this particular temperature, argon is supposed to be liquid. But in this nanoscopic confinement, it is crystallizes. So from this standpoint, this can be treated as a nanolaboratory for material science for various materials, and that's what we also actively do last years and publish in all these papers. Now, what is closer to material science, to metallurgy, the molecular dynamic simulation can be used to predict grain boundary migration. You know what is grain boundary migration in metals. And this is an important property. And what is important to calculate energy of this migration. Now, if you do this molecular dynamics for curved boundary, for plane boundary, you end up with a table. Now, on the table, on the right column, there is a numbers in EV. An actual typical value in experiments is about 1.5 EV. So molecular simulations, well, first principle simulations, so-called, they predict 30% of this energy only. So that would mean that the deeper we go, the more problems we get. And this is basically coincides with a philosophical concept that I would like to show you now. So this artificial intelligence for multi-scale materials modeling. So if we would like to do multi-scale model deterministically from the first principles to calculate everything, the entire universe from atomic behavior, it's a very decent plan, right? While we are doing this, you're supposed to increase modeling complexity. And while you do this, you're facing so-called Heisenberg principle, which is reformulated for these particular purposes. It seems that the more factors there are, the deeper and more fully the process will be described. There comes a limit when the deeper we intrude into the process, the less accurately it is described. You introduce more errors by introducing more parameters. And this is Heidelberg principles applied specifically for this purpose. So what is the bypass? It is not non-deterministic extension. So you're supposed to jump to the side and move on with non-deterministic extension of artificial intelligence and materials learning. This is a pay that we're supposed to do for the fact that we cannot go through the forest straight. And however, this gives us a lot of optimism, and Professor Wegener also advocate of this together with Professor Neugebauer. And with this, I just would like to finish with this optimistic statement of a genius of all time, Stephen Hawking, that it is surely better to strive for complete understanding of the phenomena than to despair of the human mind. Thank you.
Thank you very much, Mr. Hatov, and also that you present your paper in English language, which is not necessary to translate. It's very good. Yes, I know that everybody in Skoltech can speak English. Well, colleagues, we are going to end of our plenary session. Also, maybe some questions to our speakers, please, if you have. It's possible to do just now, because maybe next 5 years Mr. Professor Neugebauer will not in Moscow. We have a chance to ask him a question, or to Professor Konrad Wegener also. Yes, please.
Thank you for the talks. To Professor Neugebauer, I would like to know maybe what do you think about the adoption of 5G into industry in Europe or maybe even globally? How is this going? And would you predict that this transition is going to come extremely fast, comparing or taking into consideration the costs and the benefits?
It's a good question. We have at the present time, or let me say at the present time, we are too slow. We have to make pressure for the future. And what I showed, our activities in Aachen in this investigation field, it's a reality lab. It's for upscaling the technology in the industry. And I think we have to go faster in the future. It's a great challenge for competition worldwide. If you look to China, they are very active in this field. And we will realize in Germany also by the federal government a lot of transfer projects in the future. And there is a strong initiative between industry, science, and also guided and supported by the politics.
Thank you. Some more questions? One more?
And the follow-up question would then be, you mentioned that you're interested to expand also Fraunhofer institution into Russia. And you said that you have a big amount of funding is directly from industry. So that would mean that you would have to collaborate not only on an academic level in Russia, but also on an industrial level. Maybe you can share some thoughts about this?
Yes, also an excellent question for the future. What I mentioned was a vision. It was a vision. I must say this clearly. For example, when we look to the reality, we started in Moscow with a representative office I think in 2007 or 2008. We closed it by my predecessor, I think in 2010 or 2012. The reason was there was not a demand from the Russian partners. There was not a demand. We have a different culture. Fraunhofer is very strong in cooperation with the industry, what I mentioned to our model. We need 30%, and this is not only a question of money. We need 30% of the project by the industry for a high velocity, for the innovation push in the industry. And this is our mission. And when we can found this in the scientific and economic environmental, then we go and we come and we cooperate. When this is in some countries difficult, it's not only in Russia. But for example, it works excellent in the United States. It works, for example, excellent in Singapore, in Chile, in the Western European countries. But sometimes it's also not so. For example, we tried it also in Japan. In Japan, we have a lot of cooperation. Fraunhofer have every year for 20 million euros cooperation with partners in Japan. But we have not an institute in Japan. We have projects. And when we want to make from the vision, when we want to come from the mission to a real cooperation, for example in Russia, at first we need common projects. We need common projects, and from the project results must come the demand for institution.
Yeah, very good and understandable. But we need real projects, but not asking money from the government, because sometimes it's not realistic, and on the other hand, sometimes it's we can spend it for nothing. Yeah.
Andre, let me, like a joke, let me say, there are also misunderstandings in Germany. Sometimes comes colleagues from the university to the Fraunhofer Institute's leaders and say, I have here 3 excellent colleagues, but the money from the government is out. Can you finance by Fraunhofer? And we say, when you bring projects, and we can with the project make innovation push for the industry, then the people can come. But only base funding is not our job. It's also in Germany, misunderstanding sometimes.
Selbstverständlich. Okay, one more, only one more. If you have, yes, please switch on your microphone.
Dear Professor Neugebauer, thank you very much for your very interesting and inspiring talk. And maybe just a direct question that is a bit more of your personal view on the topic. You mentioned that artificial intelligence in global, not only manufacturing, may lead to a GDP increase of up to 26% in some economies over a time span of the next 5 to 10 years. Now, with you being at the forefront of biologicalization or biological transformation, the question is, this might certainly be something where we may see ourselves more still in the baby shoes of this transformation. It is more of a vision that we currently draw up, where puzzle parts are still falling together to create the overall vision and the idea. But since you have a very global view on the topic, what would your estimate on the time scale be in relation to maybe a Gartner hype cycle, or when we would start to reap the first benefits up to the more industrialized development and maybe rollout of what you would describe as the biological transformation, maybe in manufacturing, if that's not too specific, or in the global economies? Thank you.
Who was the colleague with the question? Yeah. We can better communicate. We have projects today in which we realize biological transformation. For example, the lotus effect for surfaces, for cleaning of surfaces. Some years before, there was a great hype in machine tools, parallel kinematics. Konrad Weger and myself, we have we spent a lot of activities in this field, and this was real, a kinematic transformation
if you look, for example, to elephant have two coordinate systems. He have slowly coordinate systems by his skeleton, and he have like a robot with his, was ist der Rüssel? With his, you understand, with like the tongue, no? He combined two coordinate systems, a slow coordinate system for larger ways, and inside of this general coordinate, a second one for operation of different activities. Only two examples. We work in Fraunhofer at the present time for substitute of materials by it's a special. I look for the word in Potsdam, Konrad. Not silk from the spins, other thing, for substitution of carbon fibers. We have also by transformation from biological materials, we substitute carbon fibers with a high stiffness in the future, hohe Festigkeit, with a high strength, and I think about the material. No, not spider net, from plants. Also only for materials. We have solutions for the materials. We have solutions. What I mentioned also. We use we have an institute in Dortmund for logistics, and they use the Ant algorithm for optimizing of logistics, for example. And we have, and more, I think it will be a process, step by step, to use it. But it's very interesting, and I think the economies which use at first in a larger dimension the transformation of biological optimization for technical processes will be a competitiveness advantage in the future. But I cannot say in 1 year, in 3 years, in 4 years, it's on. But a lot of companies work very strong about this. In machine tools, Konrad, you know, we work together with Morisaiki and DMG in Germany. This is also to transfer in machine tools. Okay.
Thank you, Leo. Dear ladies and gentlemen, the time is over, and it's a lunchtime, Mahlzeit for everybody, and I would like to thank you one more time for participation in this plenary session, and thank you very much, and I wish you all the best in your research and development, and of course health. Thank you very much one more time, and we are very glad to see you in Stankin, but our conference will be continue after lunch. Okay, see you.